This is Biology 223, Genetics. This is doing the homework of semester 2020. It's homework 3. This is going to be part D. What is the probability of individual 5-3 being heterozygous at loci A and B? And that means heterozygous here could mean cis or trans. So that means it could be AB over plus plus, or A plus over plus B. Both of those would be included. Okay, so issue Drosophila. So male Drosophila do not end up crossing over. So we have to keep track. First time I did the problem, I neglected that and made the problem much harder. Part D is just about A and B, so we're only going to pay attention here. Let's start by notating the genotypes of generation 1. So plus plus over plus plus. And sometimes I would take a shortcut here because the concern I have is not what their genotypes are, but of what gametes they can produce. And so I could just directly do that, for example, by saying, well, I don't care that they're homozygous wild type, I only care that they can produce that gamete. And so that would be equivalent to just notating the gametes produced, because that's what we care about. In order to calculate 5-2, 5-3 here, we need only to know the ancestral gamete genotypes. So I'm going to do that. And in this case, we have 2, so I'm going to just separate them by comma. And if I can say the ratio between them or as needed. Okay, so continuing, then some things are simple. The offspring here, so no recombination. No one in the first generation is heterozygous at any. Maybe it would have been worth doing that, so I should encourage the longhand method. So nobody in the first generation is heterozygous at 2 loci, so there's no recombination that would show up, wouldn't be visible, so we can neglect that, and the gene calculating those, determining those gamete pools is easy. Here we're going to then have this individual is going to be then A plus over plus plus, therefore only give A plus and plus plus gametes. These individuals, we can do this, let me do it up here because it's a standard. So let's look at 2-2, and it's a good idea always to label these so when one wants to go back and slips the mind exactly what one is doing, it shows up, and I'm going to do it in this order. So this individual here has parents who are both plus plus over A plus, so each can make A plus or plus plus gametes equal frequency, 1/2 versus 1/2. And so the resulting distribution of possible genotypes of 2-2 will be homozygous wild type. I'm going to do it this way, plus plus over A plus, and A plus over plus plus, and A plus over A plus. These possible genotypes, 1 to 2 to 1. And so the method that I use is, well, look, I can count this and say, look, there's 1, 2, 3, 4 plus plus, so there's 4 plus plus, and 1, 2, 3, 4 A plus. There's no crossing over. None of them are homozygous, heterozygous at more than one locus, so crossing over recombination doesn't show. Or I could do it the longhand method, which I will have to do later anyway, which is to say, where do plus plus gametes come from? They come from the likelihood, 1/2, the likelihood of being this genotype, 1/2 times 1/2, and if this genotype times 1, plus the likelihood of being this genotype, which is 1/2 times 1/2, and if this genotype, 1/2, therefore 1/2 plus 1/2 plus the time 1/2 times 1/2 times 1/2. So I would have all these terms from here, from here, from here, 3 terms, and it would turn out to be that it's going to, we're going to find out that it's going to be the same 1-to-1. So this is 1-to-1, and then the end result will be there will be 2 gametes possible, A plus and plus plus, of equal frequency. It'll be half this, half that, and then you might notice that, well, that's the same as the parents, right? That's the same as the parents. Is that weird? Is something wrong? No, of course that's the same. Because this is like Hardy-Weinberg. There's a gene pool and there's been nothing to alter the allele frequency. Therefore, it will be the same. So that's a bit of a shortcut if you're comfortable with it. So let's use that shortcut now. So we have the same situation here. Notice still we don't have 2 heterozygous loci, so still recombination won't show. So here, this individual and the sibling here will be the same, just like what we did. That's 2-2. It's also true for 3-1. It's also true for 4-1. Okay, making good progress. Here, that's easy. The he will be homozygous wild type, so can only make 1 gamete. Likewise, her. Okay. And then this one is going to be clear that the genotype, so I'm going to draw the genotype off the side of her up above to distinguish from the gametes. Okay, so this individual can undergo recombination. So far, and we've made it this far down the pedigree, and we've had no funny business. I'm going to save that for a moment. Let's do this one here. So this is 4-1. So I'm going to draw that here, 4-1, and we have A plus 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 from one parent and plus plus from the other parent. So we're going to see A plus slash plus plus and plus plus over plus plus. And so the gamete pool is going to be 3 chances of plus plus, 1 chance of A plus. And I could represent that as 3/4, 1/4. I'm going to do that because I know what happens later. So I'm going to say 3/4. And so what's the difference between saying 3-to-1 versus 3/4 to 1/4? The ratio is the same, but when I say 3/4 to 1/4, I'm having that sum to 1, and that allows me to have a checksum and to make sure I'm not doing anything wrong. So, and keeping these ratios, I can keep track. Well, it's out of 4, it's out of 8, it's out of 16. That's useful. If there's some other funny business, nobly, we know somebody doesn't have a phenotype. It might be a 2/3 issue, but most commonly, if there's any recombination in the problem, then it's a little bit easier and safer to keep track of it this way, because the numbers will get strange and they're not going to be some predictable number. So this way is safer. So 3/4 versus 1/4. Okay, so now we're getting to something a little more complicated, and we have to deal with the gametes she makes. She can undergo recombination because she has 2 heterozygous loci. So let me do her 2-5 here. So 2-5 here is she can make what she's plus A plus over plus B. So therefore she can make A plus gametes. She can make plus B gametes, and she can undergo recombination. Her during meiosis in the Drosophila female, recombination can occur, and so we can have a recombinant genotype. So we have 2 parental and 2 recombinant, and here we see 10 map units apart, which means that the recombinants here will sum to 10%, which means 5%. So it's going to be 45%, 45%, and I could do it that way, and that works, but I believe it is much easier if we do it with fractions of whole numbers, in which case this is 9/20, 9/20, 1/20th, 1/20th. I think keeping track later. So this is going to be the distribution of her genotypes. Okay, so she's going to have those genotypes, and this individual and the offspring here, the male offspring, will be these genotypes with from the male parent, the plus plus. So his genotypes here are going to be, I'll just do it, plus plus over A plus, and that'll be 9/20th chance, plus plus over B plus B, that will be 9/20th, plus plus over AB, that will be 1/20th, and plus plus over plus plus, oops, I did something wrong here, that's plus plus over there, sorry about that, over 1/20th. So those are the four possible genotypes of this individual, 9/20th, 9/20th, 1/20th, 1/20th. Okay, so the first time I did this, I did a video and I posted it, and I had to take it down because I realized I'd made the mistake of assuming that recombination occurred in him, but it doesn't. And so the problem got a little bit gnarly, as it were. And I thought, whoops, that was a harder problem than I intended it to be. But it's not that. Okay, so now what's the question? Individual 5-3. So the question is, what's the probability of being heterozygous at this? So that's actually, we only need to know, he will plus plus or A plus from female parent. Therefore, we need to know 3/4 chance of plus plus and the chance of AB from here. And there's no recombination. So it's going to be, so the chance of him being this right away, I can tell you, is going to be 3/4 here times the likelihood of this, which is 1/20th times 1/2, because if this genotype going to be 1/2. So that's the likelihood of that. And so I could just write that down directly. I'll do that. And for the next problem, I have to do it more completely. For part E, I have to continue this down, but I'm just going to write that down now. So right away, I know that for D, I'm going to say D, it's going to be AB over plus plus. So this is 3/4, right? And this one is, so this is 3/4 from here, right? And if AB over plus plus, it's the plus plus to 3/4 from this part, likelihood of 3/4 inheriting from female parent. And if AB, it must be the 1/20th chance of being this genotype times 1/2 chance of being that. So that's 1/40th, 160th. So if we get that, it's going to be 3 over 160 to be this. And for the other one, A plus over plus B, well, the A plus must have come from this parent, so that's going to be plus, so what is this A? I'm running out of time here, so let me hurry up. So that will be, where is it? The A plus came from that parent at 1/4, and the plus B comes, only possibility is from this genotype, so that's going to be chance of 9/20th times if that genotype 1/2, so that's 40th, 160th, that's also, so that's 9, I did something wrong here, whoops, did I forget to multiply that? No, that was 8, so that's 3 160th for this one, and this one will be 9/160th, and if I add those together, I'm going to get 12 160th, and I can simplify that. That's fine. Okay, so that's the, what can I simplify? Divide that by 12, so I can get 3/40th is the answer for that. Okay, I have to formally, for the next problem E, I have to stop here, and next